Super job, you guys. So, what is NASA doing to study the auroras? Well, Nikki Fox, a senior scientist at the Johns Hopkins University Applied Physics Laboratory in Baltimore, Maryland, can tell us all about it.
Why do scientists use satellite images to monitor the auroras?
In analyzing the graph, when do auroral activities increase?
What are the phases of the aurora?
This is the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. I am the operations scientist for the Polar mission. The Polar mission is part of NASA's Sun-Earth Connections fleet. Within the Sun-Earth Connections fleet, Polar has the responsibility for multi-wavelength imaging of the aurora, measuring the entry of the material into the polar regions, the flow of material to and from the ionosphere, and the discharge of the energy in the ionosphere and the upper atmosphere. Scientists use satellite images to monitor the position of the various auroral features. In particular, the latitudinal location of the edge closest to the equator of the aurora determines the amount of activity. The further the aurora moves towards the equator, the bigger the event. Also, the extent and speed of the expansion of the aurora tells us a lot about the amount of activity. The further and faster it moves, the larger the event. Polar is a unique spacecraft because it carries 4 different cameras to study the aurora. There is a high-resolution visible imager, which allows us to look at the aurora in different wavelengths or colors. In this way, we can simultaneously image the red, blue, and green components of the aurora. There is also a global imager, which allows us to look at the whole Earth at once. This camera takes pictures in ultraviolet, so we can see what the aurora is doing, even when there is sunlight in the way. Auroras do occur during the daytime, we just can't see them with the naked eye. But from the images of this camera, we can see the size of the auroral oval. For example, the following graph shows you the latitudinal auroral extent for selected coronal mass ejection events. Coronal mass ejections, or CMEs, are gigantic explosions caused by the sun that can reach speeds of millions of kilometers per hour. It takes around 3 days for a CME to reach the Earth. The vertical axis of the graph is the geomagnetic north latitude from 40 degrees to 58 degrees. On a globe, 40 degrees north latitude is closer to the equator and 58 degrees north latitude is closer to the geomagnetic North Pole. The horizontal axis represents the dates of selected CME events. From analysis of this graph, we can determine that the latitudinal auroral extent generally increased from 1997 to 2000. Be careful in the way you interpret this graph. The function appears to be decreasing. Even though the data show a downward trend, the auroral oval extended closer to the equator. For this particular graph, it tells us that the auroral activity increased. Let's look at 2 data points. From the data on January 10, 1997, there was an auroral event in the northern hemisphere that extended to a latitude of 57.3 degrees. Do you know the name of the country that the auroral oval covered? If you said Canada, then you are correct. On July 15, 2000, there was an auroral event that extended to latitude 41.2 degrees. The auroral activity was so intense that the auroral oval stretched into the southern parts of the United States. The 11-year solar cycle of the Sun reached its maximum in the year 2000, so we expected auroral activity to increase from 1997 to 2000. With all these cameras and the data we collect, we can photograph the evolution of an aurora. The evolution of every aurora tends to follow a similar sequence. We call this an auroral substorm. The following images show a typical sequence of an auroral substorm. The first image shows a quiet oval before any activity begins. This is called the quiet phase. Right before we see any bright emissions, we can observe the oval getting bigger and moves further towards the equator. This is called the growth phase. The activity truly begins with the small spot of light, or onset event, followed by the lighting up of the whole ring and an expansion to a more poleward location. The large bright region you can see is called the auroral bulge. When the aurora reaches its maximum expansion, you can see that the large bulge begins to break up and the small discrete features appear. Finally, the whole aurora dims and recovers. It will eventually return to the initial state, the quiet phase. The whole process may repeat over and over again until the activity dies out completely. Now, all the images you've seen so far have been from the northern hemisphere of the northern lights, or the aurora borealis. But did you know that there was also a southern counterpart of the aurora called the southern lights, or the aurora australis? And here we're seeing a unique movie taken by the Polar spacecraft that shows us both the north and the south at the same time. This allows us to see that the activity is occurring at the same time in both hemispheres. We call this the conjugate aurora. Now, we've seen data from many different cameras on the Polar spacecraft and learned that when you add them all together, you can learn an awful lot more about the aurora. Now we're looking at an animation which shows the polar auroral image underneath with the TIMED spacecraft flying over the top. TIMED is taking images in very high resolution, and you can see that every time the spacecraft flies through the oval, it suddenly illuminates all the fine-scale features that you couldn't see before. So now we know that when you add two data sets together, you get even more information. Now, with the addition of data from ground-based observatories and sounding rockets, we can look at the aurora with full perspective.
Okay, now it's time for a cue card review. Why do scientists use satellite images to monitor the auroras? In analyzing the graph, when do auroral activities increase? What are the phases of the aurora?